Hello and Assalamu alaikum. In this video, we are going to be talking about the OneWay ANOVA. What is ANOVA? ANOVA is actually a short form for analysis of variance. And when do we use it? As you know that we used t-test to compare means of two groups, right? To compare whether there's differences in the means of two groups. So ANOVA is used when you have more than two groups. It's used to test if there's differences in the measured characteristics between more than two groups of cases. So the objective is to test if there's difference in means between the K populations, where K is also known as your groups, number of groups or number of levels. Hypothesis would be that the group means do not differ significantly, or you can write it as such. Mean in group 1 is the same with mean in group 2, is the same with mean in group 3, so on and so forth until group K. Versus your alternative where at least one pair of means will differ significantly. Or we're saying that mean in group 1 is different with mean in group 2 for at least one pair of I and J. Okay? Here's the data presentation. If you just simply see or look at it, you're going to get a little bit overwhelmed, but actually it's pretty much straightforward, where Yij is the jth observation of the dependent variable in the ith level of the factor. What is Y? Y is actually your dependent variable scores, okay? And I would be the levels or the groups, and the jth is the observation. For example, if you take a look at the table here, so this is the factor levels. What is factor? Factor is your independent variable. Okay, sometimes it's called factors in experimental studies. So under this factor, it has K levels. We do not know the number of levels. It has K just for an example to show us. So you have your level 1, level 2, level ... until level K. And then Y11 is the number 1 observation under the first level. And Y12 is the number 2 observation under the same level. And so on and so forth. And then you have the mean for the first level, and then the mean for the second level, so on and so forth. And then you're going to get overall mean value. Okay? So n is the sample size and the in the ith level of factor. So for example, in this example, we're just showing you that say if you have a sample size of 100 for the first level, okay? So this n here is going to be Y100. And say for example, for level number 2, you have 98. So this n here is going to be Y298. Okay, so I'm going to show you an example of how the data is presented in ANOVA. Say we have an IV of training method, and then our DV would be the obvious performance, and this performance will be measured using scores. Okay, just as an example. As you know that ANOVA, we need more than we need to compare more than two groups. Sometimes these groups are also referred to as levels. Okay, so let's say the first level of the training method would be the traditional face-to-face method, and the second one would be the online method, and the third one is the control group. So the respondents that belongs in under the control group will not receive any training. Okay. So we have three groups over there. The first is face-to-face, second one is online, and the third one is your control group. So for example, we label the observation as Y, right? The scores as Y, the dependent variable. So under face-to-face, you're going to have Y face-to-face number 1, observation number 1, and then Y face-to-face number 2, Y face-to-face number 3, observation number 3. Okay, and then under online, you're going to have Y online number 1, Y, oh, what happened? Y online number 2, Y online number 3, as well as the control group Y control number 1, Y control number 2, Y control number 3, and so on and so forth. Okay, So at the end of the day, you're going to have the mean score for Y face-to-face, the mean score for Y online, and the mean score for Y control group. Okay, this is important for you to understand because later on you're going to see the calculation of variance in ANOVA. Alright, so this is what we call within group because it's under the same group, right? So the variance between number 1, the variance between number 2, those are the within group variations. But what about between group variations? So these are the between group variations, and these are the within group variations. As with other analysis, ANOVA also comes with its own assumptions that needs to be upheld. The DV should always be normally distributed in each group. Yeah. However, ANOVA is a very robust analysis. It's okay with violations of normality. We also need to assume that there's homogeneity or variance. We should not violate that. That's very important. If you violate the assumptions for homogeneity or variance, you need to run a non-parametric analysis. And then we need to have independence of observations, where observations are independent of one another and they do not rely on each other. In ANOVA, our main concern is to take a look at the F statistics, where a large F implies that possibly, there's at least one pair of means will differ significantly. Okay, do not say that the means are different, but you have to say that at least one pair of means differ significantly. And when there's a difference, when you have a large F statistics and you have a small p-value, we need to conduct a post hoc test because we need to identify which pair of means that actually differs between one another. So the results are valid if assumptions of homogeneity is met. Otherwise, we need to resort to a non-parametric test. A small F statistics imply that the difference between group means is small and hence there's no differences between the group means, okay? So this is the partitioning variations. The total variations in the n terms is also known as the SST, or total sum of squares, and it is partitioned into two components. One is between groups and another is within groups. The calculation for the between group sum of squares is also known as the SSB, and the within groups is also known as the sum of squares error. So how do we calculate this? In order for you to get the sum of squares total, it is just the sum of squares between and the sum of squares within, or the sum of squares error. So this is how you calculate the DF. For between groups, DF is just the number of groups minus 1. And as for the between groups, is the number of sample you have minus the number of groups. As for total, is just number of samples minus 1. So how do you calculate the mean squares? Why do you need to know how to calculate the mean squares? This is because you need to know where do we derive the F statistics. So F statistics formula is just the mean squares between over the mean squares error. And how do we get that? So mean squares between is calculated using sum of squares between over number of groups minus 1. Mean square error is just the sum of squares error over number of samples or number of respondents minus your number of groups. And then you're going to get your p-value there. A large F value indicated by a small p-value. Remember, whatever it is, we still need to take a look at the p-value. Implies that at least one pair of means differ significantly, while a small F value indicated by a large p-value implies that the mean do not differ significantly. The statistics of interest, as usual, we want to know how to calculate the DF. How do you get the DF? In the test possibly you're going to be asked questions like what's the sample size, but I won't give you the sample size. I'm just going to give you the DF, so you have to be able to extract the sample size. Okay, so the probability of type 1 error, or the p-value, that's going to be given by SPSS, the 95% confidence interval for the pairwise mean difference. That's a formula for that. Typically SPSS will do that for you as well, and the effect size, or eta squared. So that's how you calculate the effect size or the eta squared. Let's take a look at example number 1. A researcher wanted to evaluate the effects of 4 types of cereal. We have W, X, Y, and Z on weight gain. In a lab experiment, 20 mice were weighed and randomly assigned to one of the 4 cereal types. Weight gain was recorded at the end of the study. The data are given below. So objective is to test if there is a difference in weight gain between cereal types. Hypothesis would be, which null, there's no difference in means, versus the alternative would be at least one pair of means differ significantly. We're going to take the mice and give them cereals, right? We group them into 4 separate groups and then give them different types of cereals. One of the most important thing in experimental design is that it needs to be randomly assigned. The respondents needs to be randomly assigned into each group. So let me just open my SPSS over here. Before that, I'm going to show you the data entry first. So this is how you organize the data, okay? You just input the weight gain and then according to the cereal type, W, X, Y, and Z. Why does it become like this? You just can change from numbers to labels. We already know that, right? So let's take a look at my SPSS over here. So if you can see, mine is in numbers because everything should be coded in numbers. So if I just click there, it's going to turn into the values given. How do you do that? You just need to assign values to the numbers given, right? So go to Analyze. Again, compare means, OneWay ANOVA. So your dependent would be the weight gain cereal type is your factor. We don't need anything for contrast, but we do want post hoc. Okay, we do want the post hoc results. Okay, when equivariance is assumed, we want to key. If equivariance is not assumed, you have all this down here, but let's just take a look at equivariance assumed, okay? And then you have options. We want descriptive and we want homogeneity of variance test. We also want the means plot. Continue, okay. And then wait for the results. All right, so here are the results given. So you have the descriptives over here. You have the means and standard deviations. You also have the test of homogeneity of variance. Because this is the latest version of SPSS, they're going to give you the homogeneity of variance based on mean, median, adjusted DF, and based on trim mean. But just take a look at the mean based on the mean, okay? So you have the Levene's is 3, DF1 is 3, DF2 is 16, significance is 0.062. So did we violate our assumptions for homogeneity of variance? We did not violate it because it is not significant, okay? So this is what we want. This is the ANOVA table. As you can see, F value is 4 with a significance of 0.027. So it is significant, and we can say that at least one pair of means differ significantly. But which pair of means differ? Okay, so let's take a look at our results over here. As normal, you have to describe the mean scores first with the standard deviations. P-value is more than 0.05. Equality of variance is therefore assumed. This is how you calculate the DF. The findings, the p-value for Levene's test is more than 0.05. Equality of variance is therefore assumed. The p-value is 4.0, and with the degrees of freedom of 3 and 16, p-value of the test is 0.027, less than 0.05. Eta squared is 0.429, more than 0.15. This is the calculation for eta squared. You can it is really up to you whether you want to calculate it or not. For this class, it is okay if you don't calculate it, alright? The p-value of the test is less than 0.05. The eta squared value is more than 0.15, hence at least one pair of means differ significantly. An eta value of more than 0.15 signifies that it's actually it has sufficient power. I've mentioned this in class before, effect size, the relationship between effect size and the power analysis. So when there's a difference, there is need to identify the pairs that differ significantly. This is done using post hoc test. Okay, so post hoc test is used to produce multiple comparisons between the group means. This is what we need to look at if we want to identify which pair differ significantly. The choice of methods depend on whether equality or variance can be assumed. When there's equality of variance are assumed, you can use all this, okay? But typically we use Tukey and Sheffey. Equality of variance is not assumed. You can use Tam-Haines, T2, Dunnett's T3, Games-Howell procedures, and whatnot. Okay, I use Tukey. So let's take a look at the pairwise comparison. This is very important. The Tukey's post hoc method also produces pairwise comparisons. The multiple comparison table is given below. This is your multiple comparison table. If you take a look, this is our multiple comparison table. You can see you have to take a look at the significance, okay? So W is actually significantly different from X. So serial W is actually significantly different from serial X. And serial W is also significantly different from serial Z. But they are not significantly different from serial Y. As for serial X, it is significantly different from serial W, but not significantly different against serial Y and Z, and so on and so forth. You can see at the homogeneous subset, you can see that X, Z, and Y, they belong in the same subset number 1, while Y belongs in both subsets. And W only belongs in subset number 2. We can say that W is significantly different from X and Z, but is not significantly different from Y. And Y is not significantly different with everyone, while X is not significantly different from Z. Okay, so this is the means plot. If you can see that definitely W is significantly different from X and Z, because let's take a look at the difference. There's such a huge difference. But with W, between W and Y, they're not significantly different, probably because it's just 6 and 8. Okay, while on the other hand, X and Z, the mean score is both 5, right? So let's take a look at how. So this is how you, if you want to write it in a table format, this is how you would do it. Or you can see, if you read a lot of articles, you can see that they have a mean subset or mean subscript, okay? Where the means without the same subscript would differ significantly. We know that W is significantly different from X and Z, but W is not significantly different from Y. So Y also share the same subscript as A. X and B and Y, they are not significantly different from one another, so they share the same subscript, but they are significantly different from W. So that's why it doesn't have an A for both Y and for both X and Z. Okay. The weight gain in participants who were given serial W is significantly higher compared to weight gains of participants who were given serials X and Z. The weight gain of participants who were given serial Y does not differ significantly from the other 3 serials. That's your conclusion. It's pretty straightforward. And it's just that for ANOVA, you have to really understand your design in order for you to create a conclusion or come up with a conclusion. Okay? So this is how you write the results for ANOVA in an APA format. If you notice that the APA format always calls you to write what analysis you run at the beginning. So as you can see here, a one-way between subjects ANOVA was conducted to compare the effects of 4 types of serial on weight gain. You can see the way we write the results, you must put in the DF, okay, the p-value. Remember that when your p-value is significant, this is how we write it out, okay? But when it is not significant, you have to write the original value that you got. For example, if your p is 0.66, which is not significant, right? You have to write p equals to 0.66. When it is significant, it is sufficient for you to write p-value is less than 0.05. And then after you have run the ANOVA, definitely you because since it is significant, you need to run the post hoc comparisons. You need to identify which post hoc that you run. Indicated the mean weight gain for participants. Actually, it's not participants, yeah, actually it's mice. who are given the serial W equals to, you have to write down, or you have to write out the mean as well as the standard deviation. If you decide to include your mean in a table format, as I showed earlier, then probably you can omit this. Okay, if you have the mean in a table format, this can be omitted. If you do not have the mean in table format, you have to write out the mean as well as the standard deviation. Okay, so this is how you write the results. Let's move on to example number 2. An agricultural research student wanted to test if masses of a special variety of tomatoes, so wanted to test if tomato differ between the types of fertilizer used. So this student, he has three different types of fertilizers, and he wanted to test each fertilizers and how it influenced the tomatoes. Okay, experiment was conducted in a controlled environment. First, the seedlings were planted in 3 rows of 4 each, and then each fertilizer was randomly again assigned to the 3 rows. The weight of each tomato harvested from each plant was recorded. So the student wanted to see, or wanted to test how these fertilizers, how these different types of fertilizers will affect the tomatoes' weight. Okay, so the weights are given below. Write down the objectives, hypothesis, findings, and conclusion. Before you take a look at my objective and my hypothesis, write it out first and compare with mine, whether you get the same answers or not. If you just simply read on my hypothesis or just take a look at my objective, in the test or in the future, you would probably have difficulties to even write hypothesis. Well, hypothesis writing and objective writing is an essential skill for graduate students. If you do not have those, then what's the meaning of the postgraduate education? Okay, so you can see to test if the type of fertilizer used makes a difference in the mass of tomatoes, in tomatoes mass or tomatoes weight. There's no difference in the mean mass. At least one pair of means differ significantly. So you would want to pause here and try run it yourself before looking at my example. Okay, so you go to compare means. OneWay ANOVA, you know that your dependent is the weight, and fertilizer type would be the factor itself. Before that, I forgot if I actually labeled. No, I did not label. Okay, so fertilizer A, 14.2, 16.4, 18.1. So let me just take a look. 14, 16. So that's going to be, that's fertilizer A, that's fertilizer B, and that's fertilizer C. So just give it a value over here. 1 equals to fertilizer A, 2 equals to fertilizer B, and 3 equals to fertilizer C. Okay, just do that. And then go back to analyze, compare means, OneWay ANOVA. We already have the tomato weight, fertilizer type. We don't need anything from contrast. If there's post hoc, just run it. Okay. Options, we want descriptives, homogeneity, and means plot. Okay. It's very easy. Okay. So you have the mean scores here. That's 16, 20, and 16.5. Homogeneity or variance, Levine statistics indicates that it is more than 0.05. So assuming that our homogeneity or variance, or our assumptions of homogeneity or variance, are not violated, so it's okay for us to use ANOVA. So let's take a look at the ANOVA table. Let's take a look at the p-value over here. The significance is actually more than 0.05. This indicates that probably there's no differences. It indicates that there's no differences between the means or between the paired means. Let's take a look at the results here. Okay, p-value, your f-value is 3.580 with degrees of freedom 2 and 9. You should know how to calculate the degrees of freedom. And then the value of the test is the p-value of the test is 0.072, which is more than 0.05. Conclusion, directly straight to conclusion. Based on the p-value of the ANOVA table, there's no difference in the yield between the types of fertilizer used. However, eta squared value, if you have the eta squared value, so this is when it comes into handy, okay? If you have the eta squared value, it showed some evidence of significant difference because the eta is more than 0.15, right? You see here, I calculated the eta value. I saw it as to be more than 0.15. So probably a bigger sample is needed to confirm the difference because we only have a very small sample size of 12. Okay, probably if you have more sample, then you could detect the differences. Okay, so here's example number 3. In example number 3, a lecturer wanted to have a quick check on the understanding of basic concepts and statistics among students in 4 different classes. So he selected 5 students randomly and administered a 20-item true-false test. Objective is to test the level of understanding in statistics and whether do they differ between classes. I have already inputted my data over here. Okay, you can see the values. You can see the data view. So go to Analyze, Compare Means, OneWay ANOVA. Dependence would be marks, factor would be class, post hoc if there's any. Options, descriptive, homogeneity or variance, it means plot. Click on OK. Okay. So descriptive is very important. You need to save this descriptive. And then we have to take a look at the test of homogeneity or variance because if it is violated, we cannot use ANOVA, right? We have to resort to a non-parametric equivalent. So our homogeneity of variance is violated. So therefore, we can't use this ANOVA. We have to move on to next step. So you can see p-value is 0.044. Equality of variance is not assumed. So therefore, the rest of this doesn't really matter anymore. So our next step is to run a non-parametric independent samples. Let me bring you back to the slides for a little bit. So the non-parametric equivalent for OneWay ANOVA is Kruskal-Wallis H test. Okay, the Kruskal-Wallis H test. So just simply go to non-parametric independent sample, and then you need to customize your test. Kruskal-Wallis. Just click the Kruskal-Wallis. We don't need the Hodges-Lemon. Okay, and then you need to click. Okay, so make sure that the test fields initially. Okay, let me just reset this and show it to you. Test fields would be mark is going to go on the test field, and the class is going to be on the group. Then settings, customize your test, Kruskal-Wallis, and then I just want to run it. Okay. Okay, so Kruskal-Wallis, as other non-parametric tests, it tells you straight whether you reject or you don't reject the null. Okay, in the sample over here, it seems that it is significant. So we reject the null and accept the alternative. But how do we know which pair of means differ, right? So Kruskal-Wallis will give you the pairwise comparison of class. So you can see in the significance over here, if it is significant, just like our OneWay ANOVA, if it is significant, then that pair of means differ. Okay, so means between A and D differ significantly and A and B differ significantly. So how do we know whether A is bigger than B, or A is better than B, or A is better than D, right? So this is when you need to go back to your descriptive and have a look at your descriptive. All right, and take a look at the mean scores. So over here, p-value is 0.028, less than 0.05. At least one class differs in terms of the basic understanding of statistics. And then let's take a look at the pairwise comparison of the class. So this is the part where it is significant. We can conclude that students in class A differ from those in classes B and D. So how do we make this statement here? Students in class A have better understanding of statistics compared to those in classes B and D. How do I know about that? Go back to my mean score just now. Okay, the mean scores for students in class A is 19 as compared to students in class B, it's actually 14.6. Okay, and students in class D, which is actually 10.6. So definitely there's a stark difference over there, but A and C do not differ significantly. All right, here's exercise number 1. You need to pause the video here and then run it on your own and compare it to my answers. So for exercise number 1, a hospital admin wanted to check if the stress levels differ between nurses in 3 different wards. If they work in labor, surgical, and medical, we want to test whether their stress level differs significantly. 5 nurses were selected randomly from each ward and administered the stress test questionnaire. So you write down the objective hypothesis and run the ANOVA on the data. already have my data here. So let me just run the ANOVA values. Sure, my is number 1 is labor, number 2 is surgical, and number 3 is medical. So run my ANOVA. Compare means OneWay ANOVA. Test scores, watts, post hoc. If there's any options, descriptive homogeneity means plot. Okay, so mean score for labor is 83, surgical is 70, medical is 48. So labor is very high. Okay, it seems that labor and surgical is pretty high as compared to medical. Let's take a look at the homogeneity or variance. It is significant. So we have violated the assumptions for homogeneity or variance. We have to resort to a non-parametric analysis. So go to your non-parametric test, independent sample. Fields is going to be test scores, grouping according to wards, customized test, cross-code waters, run. Okay. So the non-parametric test asks us to retain the null hypothesis. It seems that there's no significant differences between the wards, right? So there's the answer, there's the objective and hypothesis, and you can compare. So what is the conclusion of this? So if you can see that this hypothesis test summary is a little bit different because this is from the old SPSS, and just now if you want to see the new SPSS, it's going to come out as this, okay? Right, so test is inconclusive. There's no significant differences. Probably a bigger sample size is needed to arrive at a more conclusive results. And there's your homework number 5, the final and last homework. The following are the BP measurement for a sample of doctors, nurses, and lecturers. Test if there's a differences between mean BP between doctors, nurses, as well as lecturers. I shall see you in our two-way ANOVA video. Thank you.